In this lecture, we shall introduce a very important data structure, the binary search tree. Imagine that we want to implement a set data structure. It's defined as follows. We want to maintain a collection of distinct elements and support the following operations. Insert, which inserts a given value into the set. Delete, which deletes a given value from the set. And search, which checks whether a given value is an element of the set or not. Here is one way of defining this. Data set A equals set list A. Recall again that the set on the left hand side is the type constructor, the set on the right hand side is a value constructor. The name of the new type that we have defined is set A, and it has a single constructor set which takes list A as argument and outputs an object of type set A. Here is how we might implement the three functions that we described earlier. Search, which is a function with the following signature. EQA implies A arrow set A arrow bool. Search of X and set Y, searching whether X belongs to set Y. Recall here that Y is a list consisting of elements of type A. Set is the constructor. Is just searching whether X is an element of Y, which is given by the primitive function, the built-in function lm, which checks whether X is an element of the list Y. So this is the implementation of search. Insert can be implemented as follows. Insert is a function with signature EQA implies A arrow set A arrow set A. This is the original set and this is the set that we get after the element has been inserted. Insert of X inside set Y, there are two cases. If X is an element of Y, you just return set Y. This is because we want to maintain a set of distinct elements. If X is already present, we do not have to do anything. Otherwise, you insert X in Y. This you do by the simple device of attaching X to the front of the list Y. So in the other Y's case, you define it to be set X colon Y. Here is how you might define delete. Delete is a function with signature EQA implies A arrow set A arrow set A. Delete of X from set Y is nothing but the set which is gotten by applying filter not equal to X on Y. Recall that filter is a function that applies a predicate to a list and returns all the elements of the list that satisfy the predicate. The predicate that we are giving here is this funny looking object. This is a so-called section in Haskell. Recall that not equal to is an operator, is a binary operator in Haskell. So whenever you have a binary operator, you can use it as a function by enclosing it to parentheses. Furthermore, you can use it as not just a binary function but a unary function where one of the arguments have been fixed. In this case, we have fixed the argument X and we want to check whether X is not equal to any of the elements of Y. So this section is gotten by fixing the right argument and making this a unary function. So this is the predicate that you are applying to each element in the list Y. So this function will return all those elements of Y that are not equal to X, which means that it will delete X from Y. Let us look at the running time of these operations for the above implementation. Search takes order n time, insert takes order n time, and delete takes order n time. Search takes order n time because the built-in function lm takes order n time, where n is the length of the list. Insert, as you Insert also takes order n time because first of all you have to make a search in the list. Delete takes order n time because filter takes order n time. So a sequence of n operations takes order n squared time. And we might want to do better than this. We can do better than this if the elements are ordered, but storing these elements as a sorted list is not the way to go. We need a much better data structure. And that brings us to a binary search tree. A binary search tree is another way of implementing the set data structure. A binary search tree is just a binary tree that we discussed in the last lecture. It stores values of type A where A belongs to the type class ORD. So a binary search tree makes sense only for values that can be ordered. The crucial property of the binary search tree is that at any node in a binary search tree, values in the left subtree are smaller than the current node and values in the right subtree are larger than the current node. And this holds true for every node in the binary search tree. Here are two examples of binary search trees which consists of the elements 1 to 6. Here is one tree. This tree has root 4 and left subtree consisting of the nodes 1, 2 and 3, right subtree storing the values 5 and 6. Notice how the binary search tree property holds true in this tree. Every node in the left subtree has a smaller value than the root. So the left subtree has values 1, 2 and 3, the root has value 4. Every node in the right subtree, namely 5 and 6, has value greater than 4. And recursively in this left subtree, the same property holds. 2 is greater than 1 and 2 is smaller than 3. Similarly here, 5 is smaller than 6. Here is the other tree which represents the same elements. This tree has root 3 and the left subtree has the nodes 2 and 1. In the left subtree, 1 is to the left of 2 as it ought to be, and the right subtree has the nodes 4, 5 and 6, and this itself satisfies the search tree property because 5 is the root whose left child is smaller than 5 and whose right child has a value that is greater than 5. We define binary search trees as follows: data S tree A equals nil or node S tree A S tree A. This is exactly similar to the definition of binary trees that we had earlier. And we derive EQ, OR, show, etc. We might create our own instance of the show method, or we can just use the default show function. Just calling this S tree does not make it a search tree. We could have objects of type S tree which completely violate the search tree property. So here is a function that takes a search tree as input and tells whether it is indeed a search tree or not. It takes a binary tree as input and tells whether it is indeed a search tree or not. So this is a function is S tree whose signature is ORDA implies S tree A arrow bool. Is S tree of nil is just true because the empty tree obviously satisfies the binary search tree property. Is S tree of node T1 x T2 is nothing but is S tree of T1. The left subtree should recursively satisfy the search tree property. The right subtree also should recursively satisfy the search tree property. So is S tree T1 and is S tree T2, and you have to check whether all the values in the left subtree are smaller than x. One way to check it is to check whether the max value in the left subtree, max t of T1 is less than x, and we also need to check whether all the values in T2 are greater than x, and one way of checking it is to check whether x is less than the minimum value in T2, x is less than min t of T2. But we add an extra clause here. because the max t function that we will define later is defined only for non-empty trees. So you say either t1 is nil or max t of t1 is less than x, and either t2 is nil, but in case it is non-null, check if x is less than the minimum value in the tree t2. This is the definition of is search tree. The maximum value in a tree is computed as follows. Max t is a function with signature OR A implies S tree A arrow A. In this function we assume that the input tree is non-nil. Max t of node t1 x t2 is nothing but max of x and max of y z. Here y is supposedly the maximum of t1 and z is supposed to be the maximum of t2. But t1 could be empty. Therefore, the definition of y is slightly more complicated. Y is defined to be just x in case t1 is nil. Otherwise, it's defined to be max t of t1 recursively. And z is defined to be just x in case t2 is nil. Otherwise, it's defined to be max t of t2. Symmetrically, you can define the minimum value in a tree also. Min t, which is a function with signature OR A implies S tree A arrow A. Again, we assume that the input tree is non-null. Min t of node t1 x t2 equals min of x and min of y z. The minimum of these three values, where y is x in case t1 is null, otherwise it is min t of t1, and z is x in case t2 of nil, t2 is nil, otherwise it's min t of t2. Now let's look at an important function on tree, namely searching for an element in a tree. Let's say we want to search for the element 34 in this tree. This tree consists of the nodes 41, 23, 17, 34, 51, 62. As you can see, this is a search tree because it satisfies the search tree property. Every value in the left subtree is smaller than the root, and every value in the right subtree is greater than the value at the root, and recursively this property holds for both the left subtree and the right subtree. So searching starts at the root of the tree. We check whether 34 is the same as the value 41. In this case, we see that 34 is not equal to 41, but we also see that 34 is smaller than 41, and therefore if the value 34 is represented in this tree, it has to lie in the left subtree, because the value we are searching for is smaller than 41 and it cannot lie in the right subtree. Therefore we go left and we check whether 34 is equal to the value in this node. The value in this node is 23, which is larger than 34. And now we know that if 34 were to be present in this tree, it has to be in the right subtree of this node, because to the left of this node, all values are smaller than 23 and therefore smaller than 34. So from here we go right. And here we see that the value is indeed 34, which is what we were seeking for. So we stop at this point. Let us say we are searching for 49 in the same tree. Now 49, again we start the search at the root. Now 49 is greater than 41, so it has to lie in the right subtree. So we go right. The value that we have to examine now is 51, and 51 is greater than 49. So 49, if it exists at all, has to lie to the left of 51, but there is no element to the left of 51. So this search ends in a failure, and we say that 49 is not present in the tree. So here is the strategy for searching for an element in a tree. We are searching for a value v in a search tree. If the tree is empty, we report no. If the tree is non-empty, then we do a case analysis. If v is equal to the value at the root, we report yes. If v is smaller than the value at the root, we search in the left subtree, which could be empty, in which case we would report no. If v is larger than the value at the root, we search in the right subtree. Again, this could be empty, in which case we would report no. Here is the code that realizes the above strategy. Search, which is a function with signature ord a implies stree a arrow bool. Search nil v. If you are searching for the value v in the empty tree, then the output is false. Search of v in node tlxtr, this is the tree with left subtree tl, right subtree tr, and value at the root equals x. Here there are three cases. In case x is equal to v, then we say true. In case v is smaller than x, then we search in the left subtree, search tlv. Otherwise, we search in the right subtree, search trv. The worst case running time of this procedure is proportional to the length of the longest path from root to a leaf, because we start at the root and keep descending the tree till we reach a leaf, or we reach the value that we are seeking for, but we are talking about the worst case. And the length of the longest path from root to a leaf is nothing but the height of the tree. So in the worst case, the running time of search is proportional to the height of the tree. Here is the other important function that we wanted to implement, inserting an element in a tree. Let's consider the example of inserting 33 and 48 into this tree, the same tree that we considered earlier. To insert 33 and 41, we first need to determine the location where 33 should go. So we start to search for 33 in the tree. We start at the root and compare the value 33 with the value at the node, which is 41. 33 is smaller than 41, so we descend along the left subtree. Now 33 is greater than 23, so it should, if it were present in the tree, it should lie in the right subtree. So we descend right. Now we see a node 34. 33 is smaller than 34, but there is nothing to the left of 34. If 33 were present in the tree, in the subtree starting from 34, it should be present at the left of 34, but there is nothing to the left of 34. So this tells us that the element 33 is not present in the tree and we can add it. And the most natural place to add it is, in fact, the only correct place to add it is as the left child of 34. So we add it there. Now let's consider 48. We again check with 41. 48 is greater than 41, so we descend down the right subtree. 51 is greater than 48, so we have to descend down the left subtree, but there is nothing in the left subtree. So this again tells us that 48 is not present in the tree, so we add it as the left child of 51. So this is the overall strategy for insert. To insert a value v in a search tree, you search for v in the tree. If v is in the tree, there is nothing to do. If not, add a node with value v at the place where v is missing. And the place where v is missing is found by the search routine. If the tree is empty, you create a node with value v and empty subtrees. If the tree is non-empty, if v is the value at the root, you exit. If v is smaller than the value at the root, you insert v in the left subtree. If v is larger than the value at the root, you insert v in the right subtree. Here is the code that realizes the above strategy. Insert, which is a function with signature ord a implies stree a arrow stree a. Insert nil v equals node nil v nil. This is a node with root v and two empty subtrees. This is what happens when we insert v into the empty tree. Insert node tlxtr v. We are inserting v into a tree with root x and left subtree tl and right subtree tr. If x is the same as v, then we just return the tree, node tlxtr, because there is nothing to do. If v is smaller than x, then we go down the left subtree, node insert tlv xtr. Notice that we modify the left subtree by inserting v into tl, and then we make that new tree as the left subtree of the overall tree. So you first compute insert TLV and then make that the left tree of this tree, which is given by node insert TLV x tr. Otherwise, which means that v is greater than x, you insert v in the right subtree, node TLX insert TRV. Again, in the worst case, the running time of this routine is proportional to the length of the longest path from root to leaf or the height of the tree. Let us now consider deletion from a tree. If you want to delete v from the tree, if the tree is empty, we can just exit because there is nothing to delete. If the tree is non-empty, then if v is smaller than the value at the root, then you delete v from the left subtree as usual, because v is evidently not the value at the root because v is smaller than the value at the root, and v cannot lie on the right subtree. Therefore, v has to lie in the left subtree, and we descend down the left subtree and delete v. If v is larger than the value at the root, we similarly delete v from the right subtree. The important case is when v is equal to the value at the root. For example, let's consider the tree with root y, left subtree consisting of the node x and its subtree is t1 and t2, right subtree being the node z with left subtree t3 and right subtree t4. Now, if we want to delete v, we have to remove y from this tree. But if we remove y, what node should replace y? Is it x or z or something else? One can easily see that it is not possible to blindly push x or z up the tree. This is illustrated in the following example. Suppose we want to delete 41 from this tree. This is the tree that we considered earlier after we have inserted 33 into that tree. Suppose we want to delete 41 from this tree. We cannot shift 23 up because there is a conflict with the value 34. 34 earlier it was in the right subtree of a node having the value 23, but now it is part of the left subtree of the root and the root has value 23, and any node in the left subtree has to be smaller than the value at the root, and if we push 23 up the tree to the root, then there is a conflict between 23 and 34. Can we therefore push 51 to the root? We cannot shift 51 up to the root because there is a conflict between 51 and 48. Again, 48 lies in the right subtree of the node which contains the value 51, and according to the search tree property, 48 has to be greater than 51, but 48 is smaller than 51. So there is a conflict again. How do we resolve this conflict? As we saw earlier, we cannot blindly push x or z up this tree. The solution is to move up a value to the root that is larger than the left subtree and smaller than the right subtree, which means either the maximum value in the left subtree, which will lie somewhere here, or the minimum value in the right subtree, which will lie somewhere here. So we should pick a value which lies somewhere inside T2 and replace y with that, or we can pick a value which lies somewhere within T3, the smallest value in T3, and replace y with that. To consider the same example again, suppose we want to delete 41 from this tree. We remove 41. And we find the maximum value in the left subtree, which is 34, and we move 34 up to the root. But now this leaves a hole at the position where 34 was. One can argue that 34 cannot have a right subtree. If 34 had a right subtree, then there would be a value that is larger than 34 in the left subtree of the original tree. Therefore, 34 will not have a right subtree, it can only have a left subtree. We can push the left subtree up to occupy the place of 34. In this case, the left subtree consists of a single node 33. So, we move 33 up to occupy 34's position. So, here is how we delete the maximum value. Keep going right till you reach a node whose right subtree is empty. From x, we keep going right till we see y here, and then we see a z here whose right subtree is empty. At this point, we know that we have found the maximum value in the tree whose root is x. Now we remove this node. Since it does not have a right subtree, we do not need to worry about that. We just push tz in the place of z. This is how we delete the maximum value of a tree. Here is the code. Delete max is a function whose signature is ORDA implies S3A arrow the pair A comma S3A. Delete max, as you see, returns both the maximum value of the tree as well as the modified tree after having deleted the maximum value. There are two cases to consider. Delete max of node TL x nil is the first case. This is the case where we are already at the rightmost node. Then we know that x is the maximum value, so we return x, and we have to return the modified tree after deleting x. In this case, x is the root, we have deleted x, and there is nothing to do, so TL is the tree that you get after deleting x. The other case is when there is a non-null right subtree. Delete max of node TL x tr, where tr is a right subtree which is not equal to nil, is y comma node TL x ty, where y is the maximum value in tr and ty is the tree that you get after deleting y from tr. So delete max of node TL x tr is the pair y comma node TL x ty, where y comma ty equals delete max of tr. Having defined how to delete the largest value in a subtree, let's return to the original task, which was to delete an element from a tree. Delete is a function whose signature is ORDA implies S3A arrow S3A. Delete nil v equals nil. If you want to delete v from the empty tree, you do not have to do anything. Delete node TL x tr v. This is a non-trivial tree. In case v is smaller than x, then you delete v from TL, from the left subtree. So in case v is smaller than x, the result is node of delete TLV x tr. In case v is larger than x, the result is node TL x delete trv. Otherwise, this is the case when v is equal to x. If TL is the empty list, if the empty tree, then you have a tree whose root is x, whose right subtree is tr and whose left subtree is empty, and you are deleting x. There is nothing to do, you just return tr. Else, you have a tree where x is the root, the right subtree is tr and the left subtree is tl. You delete the maximum from tl and that will give you y comma ty. The maximum element is y, ty is the tree that you get after deleting y from tl, and the new tree that you form is nothing but node ty y tr. Recall that our strategy is to find the maximum element in the left subtree and replace x by that value. So y is the maximum element in the left subtree, we replace x by y. So y becomes the new root, ty is the new left subtree, and tr is the right subtree as usual. Again, in the worst case, this code runs in time proportional to the height of the tree. Here are some other useful functions. Make tree, which makes a tree from a list of elements. The signature is ORDA implies list A arrow S tree A. Make tree is nothing but fold L insert nil. Recall that fold L is a function that takes a function as the first argument, an initial value as the second argument, and then applies this function repeatedly on a list that is given as input by using this as initial value. So the initial value that we give is the empty tree denoted by nil. So what this will do is it will first insert the first element of the list into the empty tree, then it will insert the second element of the list into the resulting tree, it will element the third element into that tree, etc. So this will achieve the effect of inserting all the elements in the given list into the tree, into the empty tree. So it forms a tree with all these elements. Inorder is another useful function. Inorder of nil is nothing but the empty list. Inorder of node TLXTR is to recursively print inorder the left subtree and then print the root and then print inorder the right subtree. This is called inorder because the root is placed in between the inorder of the left subtree and the inorder of the right subtree. You can observe that inorder T prints out the values in the tree T in ascending order, and therefore one way to sort a list of integers or a list of any values of type RDA is to make a tree with that list and then apply the function inorder on the tree, which we define as inorder dot make tree. The dot syntax in Haskell allows you to compose two functions. So sort is the composition of inorder and make tree. So in summary, binary search trees can be used to store a set of elements and support the operations insert, delete and search. It's a fundamental data structure that is widely studied. Insert, delete and search takes time proportional to the height of the tree, but the height of the tree can be as large as the number of nodes in a tree. So we will see how to improve this in the next lecture.